Hello and welcome to the Tech Hearth. I'm Ryan, and today we're going to be talking about radiation detectors and how they work. And to do that, I came out here to the very wet and windy and cold New Mexico desert at the White Sands Missile Range, because just over there, the first nuclear bomb was exploded on July 16th, 1945. The Trinity test was the culmination of thousands of scientists working for years to build the first nuclear bomb, and in a very real way, the shockwave from the explosion of the gadget continues to affect us today, shaping art, politics, and society. But there's another, more tangible way that we can still sense the remnants of that explosion, and it's right here at the ground beneath my feet. This is trinitite. It was created in the first few seconds after the explosion, when the blast pulled desert sand, the test tower, and around 10 pounds of unconsumed plutonium up into the fireball and superheated it to around 2,700 degrees Fahrenheit. All that debris melted together and rained down as molten glass onto the crater. Due to how it was created, trinitite is mildly radioactive, though not enough to be dangerous. But if I hold up a radiation detector to it, like this Radiacode scintillation detector, we can, in a sense, still hear part of the Trinity explosion continuing today in the form of radioactive decay. But how do radiation detectors work? And why am I saying radiation detectors instead of Geiger counters? For answers to that, we'll have to go back inside.
Whoa, okay. It's a lot warmer and less windy back here in my office. Okay, so let me answer the second question first. I'm not calling all radiation detectors Geiger counters, because many of them aren't Geiger counters. A Geiger counter, like this one, is a specific type of detector, which uses a high-voltage, gas-filled Geiger-Müller tube. When the gas in the tube encounters a particle of radiation, it ionizes and produces an electric charge that can be amplified and read by the meter. After the gas has ionized, it needs to be reset or quenched, which means that there's a short period of time after each detection where the meter cannot detect another particle of radiation. As a result, Geiger counters can only detect radiation up to a certain limit, and then they become saturated and cannot measure anything higher. They also may not be able to measure alpha radiation or very low levels of radiation due to their design. This means that they can't really be used to measure traces of radiation, such as small levels in well water or radon levels. Fortunately, we have other types of radiation detectors that we can use. Another common type of radiation detector is called a scintillation detector, like this Radiacode one that you saw me use in New Mexico. Scintillation detectors use a crystal, which can be very small like the one on this device, or very large like this one I found at the National Museum of Nuclear Science and History in New Mexico. When struck by radiation, the crystal emits visible light, which is picked up by a photomultiplier and converted into an electrical signal that can be read by the detector. Scintillation detectors can be far more sensitive than Geiger counters and can detect very low levels of radiation, including detection and measurement of radon, as with this model of radon detector here, which uses a scintillation detector tuned for alpha radiation associated with radon decay. However, as with Geiger counters, they can be overloaded. Since the crystal actually flashes when struck with radiation, there can be overlaps in the flashes in high radiation environments. The photomultiplier can also be overloaded, causing inaccurate readings. When trying to measure high levels of radiation, the most common type of instrument is an ionization chamber. Unfortunately, unlike with the last two types, I don't actually own one of these. Ionization chambers directly read the electric current produced when radiation ionizes gas within a tube. It's similar to how a Geiger counter works, but unlike a Geiger counter, it's not counting pulses, but instead measuring the electrical current produced by the ionization process. This means it's ideal for measuring higher levels of radiation, like those found in a laboratory or after a nuclear weapon is detonated, but not very good for measuring lower levels. There is another type of relatively common radiation detector, and that's the semiconductor detector. Semiconductor detectors are used in spectroscopy in laboratories, for medical imaging in hospitals, and for radiation surveying. They work similarly to a camera sensor, where radiation striking the sensor causes charge differences, which can then be measured and analyzed. Unfortunately, as with a camera sensor, they are prone to noise. The materials they use are optimized for high energy particles, but they must be kept very cold to keep thermal noise to a minimum. As a result, they're much less portable than the previous three types of detectors. There's one more form of radiation detector I haven't mentioned yet, and that's the dosimeter. There's a few different types of dosimeters: film, similar to this one, electronic, thermoluminescent, and a couple of others, but the focus of this video is on detectors that provide more real-time information than many dosimeters do. So what can radiation detectors tell us, and how can we use them? Let's look at the two types that I have here: a Geiger counter and a scintillation detector. The Geiger counter can basically just tell us roughly how radioactive something is and is good for some basic measurements. The scintillation detector can do more in-depth measurements and analysis and can help us start to identify things like isotopes, which can tell us what is around us. Let's look at them in action. If you remember the trinitite I had back in New Mexico, that was mildly radioactive glass. Most of the glass was scraped up by the military and buried as radioactive waste, and anything remaining at the site today is property of the US government and cannot legally be removed from the site. However, a few barrels were sold off before that point, so you can still legally obtain trinitite from suppliers such as United Nuclear, which is what I did several years ago. We can see if we bring the Geiger counter over the trinitite that it doesn't seem to do much. And that's because trinitite primarily emits beta radiation, not gamma radiation. If we open the testing window on the Geiger counter's wand, we can bring it back over the trinitite and see that we're getting about 100 counts per minute, or under 0.2 millirentgen per hour. And since we had to open the shielding on the probe, we know that most of that is beta radiation, not gamma radiation. That corresponds to about the same amount of radiation in an hour that you'd get from being in Denver for a day, and about 1/3 as much as you'd get in a dental x-ray. I will note that this Geiger counter hasn't been recalibrated in a few years, so it's not going to be perfectly accurate, and it's going to miss radiation due to the quenching effects that I discussed earlier. That said, we can still get a rough estimation of how radioactive something is from it. Similarly, we can test this uranium ore and see that it is far more radioactive than a trinitite, though also not to particularly dangerous levels, even if it does make my Geiger counter click a lot. I've closed the shielding on the probe to block out beta radiation, and we can see that we're getting around 200 counts per minute of gamma radiation when we're right against the rocks. That's around 0.3 millirentgen per hour of gamma radiation. That's useful if we need to know generally how radioactive something is, but not very useful if we ran across something and wanted to know what it was. And that's where a scintillation detector comes in handy. Because the flash produced by the scintillation crystal varies in intensity with the energy level of the radiation hitting it, it's possible to determine which isotope emitted the radiation. If we put the Radiacode over the trinitite and leave it for a while, we can start to see a spectrum being built up, with peaks for cesium-137 and americium-241. There may be smaller peaks for some of the other isotopes that were generated by the blast, but many of those are much shorter lived and have since decayed away. We can also see that the Geiger counter was missing some of the radiation that's present in the trinitite, with the scintillation detector showing about 250 counts per minute. After running the Radiacode for a bit, it said it was averaging around 65 nanosieverts per hour, which is far, far less than the Geiger counter was measuring, even though we did just switch measurement units. This is down to the way that scintillation detectors measure radiation. The dosage that they measure is based on how energetic the particles of radiation are. Gamma radiation is far more energetic and contributes to a much higher dose, while beta radiation contributes much less. Geiger counters are unable to distinguish between the two, so when we were taking our readings with the shield open, it told us that we had a much higher effective dose rate than we actually did. Scintillation detectors can detect the energy of the particles that they're measuring, so they will show a lower dose overall. Let's do the same for the uranium ore. We can quickly see peaks for the decay chain of uranium. We can also see that counts are much higher than shown on the Geiger counter. The maximum count rate that I saw was just a hair over 5,000 counts per minute, which is quite the difference from the trinitite. That's a maximum dosage rate of 1.9 millisieverts per hour, which is a little under half the dose that you get from a dental x-ray. So if you stayed next to this for a little over 2 hours, you'd get the same dose that you'd get from a dental x-ray. That level of dosage is safe if you're not constantly exposed to it. I should mention here that everything in my collection of radioactive objects are securely locked up in a safe when I'm not doing something that involves them, to prevent accidental or long-term exposure. In practical usage, you can get a lot more detail out of a scintillation detector than you can a Geiger counter. But the Geiger counter can still be handy when you're surveying a large area and need to know where radiation is present. I hope that this was an interesting and informative look at radiation detectors, some of their strengths and how they can be used. If you liked it, hit like. If you have any questions, or if I didn't cover something that you wanted me to talk about, or you want to just know more about something, put it in the comments. I'd love to do a follow-up to this to answer any questions that there might be. And coming up next time, I'm returning to my Meshtastic series. I'm going to show you how to plan a multi-node deployment, including predicting coverage of your nodes, and how you can manage them remotely. If that sounds interesting to you, don't forget to subscribe so that you don't miss out, and be sure to join me again here at the Tech Hearth.